So on homework question 13.35, 3.6, and 3.7 all refer to this first slide. They all refer to this first image here and this hypothetical reaction where we have x2 breaking down to give us 2x. And so this is x2 right here, right? There are two molecules of x together in x2. And it's asking us what is the half-life in seconds of this decomposition process. Half-life is determined as the time required to cut the concentration of the chemical in the reaction in half. So the first thing we would do is just count to see an approximate concentration that we have at time 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. We see that 5 seconds later, I have 1, 2, 3, 4, 5, and 6. And 5 seconds after that, I have 1, 2, and 3. Right? So the half-life, the time required to cut the concentration in half. To make our lives easy, let's say that this Erlenmeyer flask is a 1-liter flask. So we can directly take those 12 molecules and say, okay, I have a 12 molar solution here. That goes to 6 molar at 5 seconds and then 3 molar at 10 seconds. So we were fortunate in this problem that they gave us nice, neat numbers that fit nicely into that half-life time frame of going from 12 to 6 to 3. Right, we would have had a different calculation on our hands if we had to go from, say, 12 molar to 10 to 7 to 5 to 3. That would have been a much different calculation. That calculation is certainly doable. This calculation was nice and neat in that we have these nice 5-second half-lives in this reaction, right? So our answer, 5 seconds. But we need this information for the next two calculations. The next two calculations, right? Question 36 and 37, what is the value of the rate constant for this reaction, right? So we got a little bit of information from the previous slide that I didn't point out previously. This is important right here. The reaction follows first order kinetics. So this is telling us the equation that we can use to relate concentration changes in time. Because it's a first order reaction, we will need to use the integrated rate law for a first order reaction. The integrated rate law for a first order reaction is the natural log of concentration at time t. So time t is any time in the future equals negative k, that's the rate constant, times time of the reaction plus the natural log of a at time 0. Right, so a at time 0 is our initial concentration. A at time t is our concentration at some point in the future. So we know two of those values, right? We know at time 0 we had 12 molar. We know at time 5 seconds we had 6 molar, right? So that's part of our calculation. And because this is a half-life question, we can calculate it this way. This way would be the hard way, the long way. We can also calculate it using the equation that represents half-life for a first order reaction. For a first order reaction, half-life is represented as T1/2 equals 0.693 over K. As you can see, this is a much easier calculation because we know half-life. 0.693 is given to us. We are looking for rate constant. Rate constant is K. So let's take the easy route. Right, T1/2 equals 0.693 over K. From the previous slide, I know that my half-life is 5 seconds. So 0.693 over K. I'm going to multiply both sides by K. K cancels out. And I have 5 seconds times K equals 0.693. Going to divide by 5 seconds on both sides now to get K by itself. K cancels or 5 seconds cancels out, and K, my rate constant ends up being approximately 0.139 inverse seconds. For a first order reaction, the units on rate constant always should be inverse seconds, 1/seconds. Now that I have that information, now I can tackle question 37. And this is one of those more challenging ones where we don't have a concentration that falls on a nice timeline, a nice half-life timeline that fits into our previous data. So for question 37, how many X molecules will be present after a total of 8 seconds into the reaction, right? So our half-life is 5 seconds. We're not asking for 5 or 10 or 15 seconds. We're asking for 8 seconds into the reaction, approximately how many molecules would be there. Now we need to know, we need to use the integrated rate law for a first order reaction. So we've got the natural log of concentration at time t. That's our unknown, right? We want to know at 8 seconds, that's time t, 8 seconds into this reaction, what's our concentration? Minus kt plus natural log of A0, right? So AT is our unknown. We know our rate constant. Our rate constant is 0.139 inverse seconds. We know our time is 8 seconds into the reaction, and we know that our initial concentration from the data previously presented was 12 molar. So we can see in this calculation, right, I'm going to multiply 0.139 times 8 seconds, and I'm going to take the natural log of 12. And so I get the natural log of concentration at time t equals a negative 1.109 plus 2.4849. You might be wondering about units at about this point. And if we take a quick look, right, seconds cancel out here. And whenever we're taking natural logs, there are no units associated with that. So yes, there should be a 12 molar associated. There should be a molarity associated with 12. But whenever we do a natural log, we do not have units associated with that number. The final answer should be concentration, should be molarity, even though we don't include units in that calculation. So we add this across, right? Negative 1.1 plus 2.4849, and we get approximately natural log of concentration at time t, which is 8 seconds, equals 1.376. Is this your final answer, right? No, this isn't our final answer because we are asked what is concentration. We just wrote out the natural log of concentration equals 1.376. So that's the natural log of what concentration is. That is not the concentration. So one little trick to get to concentration, right? We have ln of x, right? X is our unknown, x2 in this case. Well, if you take e to the ln of x, that equals x. So in this case, all we're doing is plugging this value, right? We know ln of x equals 1.376. We're going to plug that value in here. So e raised to the ln of x equals x. In this case, x is our concentration. And this is little e, right? So e raised to the 1.376 equals a concentration of approximately 3.96. And the question asks for the nearest whole number, right? The nearest whole number would obviously be about 4 molecules in this reaction, 8 seconds into the reaction. So this little trick right here will be important. It will come back. Our way of getting out of ln of x equals is e to that value will give us back the x that we're looking for. Will give us back what is that concentration. And if you're ever unsure, right, if you're not sure mathematically if you made the right steps, all you would have to do is just take the natural log, right? If you took the natural log of 3.96, right, it should give you back 1.376, just to make sure, right, to check mathematically, did I do the right steps in the right order, right? That should check for you. So we're looking at 4 as our final answer, 4 molecules at 8 seconds into the reaction.